So can you hear me, or should I use the microphone? I should use the microphone. Maybe you should use the microphone because I can't hear you. Okay, let's try also this. Okay. Okay, so this is the first time ever that I use the microphone. So hearing my own voice in the loudspeaker, it's really funny. Very good. Let's open this. Here. Slideshow. Nice. So, hello everyone. My name is Alessandro Redondi, as you can see here. I'm your basic lecturer, let's say, for the tutorials on programming the Internet of Things. Okay? So, you get some... What's happening? Okay. Stay there. So you have some details here on this slide. This is my office, actually my current office. It's in the building in Lambrate, okay? 10 minutes walking from here. Now, we are relocating all the offices, so probably this address may change in the next month. I will notice you when we change our location. Anyway, if you need anything, like if you have any issues on what we will see during the next lessons, just send me an email. You can use this address here. I guess that it is also on the website. Or you can try to reach me at this number. The probability of having a success with this way of communicating are very low, okay? So because I'm always maybe here or there or somewhere else doing my stuff, okay? So the email is the most reliable way of contacting me, okay? First of all, I just need some, let's say, statistics from you, okay? So I would like to know how many students are from the 4th year, or let's say the first master year. Okay, so basically most of all. Probably this has to do with overlap with other courses. And how many are from the telecommunication, let's say, branch? Okay, how many from the computer science? Okay, so 50-50, more or less. And some other interesting statistics for me are how many of you are, let's say, how many of you know at least one programming language? Or at least they know how to program a very, very little program. Okay, everybody, I guess. Except you and your colleague. Why? I mean, at least something in C you should know that. Very, very basics. Okay, because most of the things that we will see in these lessons are basically programming exercises. Okay, so we will learn how to actually develop and program applications for the Internet of Things, and as you can imagine, most of the stuff that we will see is based on some programming language, okay? We will see TinyOS, which is basically based on C. We will see also a little bit of Python and Java involved in the process, okay? Very, very basic stuff. I don't want to scare you. It's very, very straightforward stuff. Most of the time it's just to reuse or slightly modify a pre-existing template, okay? So you don't have to become gurus of a particular programming language, but you need to be a little brave, if you know what I mean, okay? You really need to try the exercises that I will show you, the examples that I will show you, okay? Most of the stuff is based on C-like programming languages. Okay, that will become even more clearer when we go through this set of slides. But we will also look at some more high-level examples. For example, in the second lessons, which will be after the Easter break, we will see how to use these tools for putting the data that we collect from a sensor network on the cloud. And as you can imagine, we will use something which is more related to web-based programming, okay? But still, very, very simple examples, okay? Very, very straightforward approaches. You don't have to be scared. You just have to be brave enough in order to try and play a little bit with the things that we will see, okay? So even if you do not know how to program a big program or a complicated program, give it a try, okay? I don't want you to lose you soon. Anyway, let's start. So what are the objectives of these classes? Well, basically, I will give you an overview of the software that is available to develop and program applications for the Internet of Things. Okay, so we will start with basic examples, and then we will see different approaches and how we can use one, when we should use one, when we should use another one, and so on and so forth. And of course, I would like to stimulate your curiosity. Okay, so let's try to have a high level of interactivity here. Okay, if you have any question, raise your hand. If you have any doubt or issue, or even just a curiosity, okay, raise your hand and we can discuss a little bit. I will give you basic tools, okay, to develop applications. You know, you always have to keep in mind that the Internet of Things is not a standard. It's not something that is there and we have to use it. Okay, it's a creature which is continuing evolving. Okay, it's not yet done. There's a lot of stuff to be done. So also the tools that we use to program the Internet of Things are not standards. Okay, so there are a lot of programs out there to be discovered, to be used. And we will look at probably the oldest one, okay, the one that have been around for long now, maybe 10 years. But there's a lot of stuff which keeps coming in, okay, so at least if I can give you a little bit of curiosity, then you can go on your own and discover what's new and what you can use, and so on and so forth. Of course, I want to stress this out a lot. I will repeat this sentence probably 2 or 3 times per lesson, but since the time we have is limited, because we have only 6 or 7 classes, I mean, with me, it's really important that you start as soon as possible to play with all these tools that I will present, okay? And to try to maybe practice a little bit, run some examples, maybe try to modify here and there a little the code to see what happens, and so on and so forth, okay? Of course, the sooner you start, the better it is for you, okay? So this is, let's say, tentative calendar of our next classes. So today it's basically an introduction, okay? So I won't enter into details. I will just give you an overview of what's available. Then we will meet next week after the Easter break. So I take the opportunity. Today the university is closed. Sorry, tomorrow the university is closed, okay? So there's no lesson, basically. So next week we will see this Xively, and it's basically a web-based application that is needed to put your data that you collect with, for example, a sensor network on the web for being easily accessed and managed, and so on and so forth. And then we will move to the operating systems for wireless sensor networks. So we will spend 2 lessons on TinyOS. TinyOS is, I would say, the most famous operating system for wireless sensor networks. And then we will look at Contiki and Motrunner, which are 2 other operating systems. The first one, Contiki, has been used in a lot of commercial projects. Okay, so most of the, so let's say TinyOS is basically used for research purposes. Okay, so for testing new protocols, testing new applications, and so on and so forth. Contiki has been used a lot in commercial applications. Okay, so if you go on the Contiki website, you see a lot of examples of actual deployment of sensor networks and application of the Internet of Things, which actually work now. Okay, and then we will see Motrunner, which takes basically a completely different approach in the sense of how the operating system is structured. But I will enter into the detail of this later. And then I will use the last lesson to basically present or to explain the projects that you guys are going to implement, okay, as a requirement for passing this exam, okay? And I will be more specific on the projects later, okay, during the course. Good. Any questions so far? No? Okay. Let me check the time. Very good. Now, I usually like not to sit down while I speak, but since I have to record my voice for the other colleagues of yours, it's better that I sit down so that the voice is clearer on the video. So, well, anyway. Okay, so let's start with an overview on the Internet of Things, okay? Probably you have seen these slides already with Professor Cesano, but it's good to see them again, just to, stress out the concepts, or at least the main concepts that are useful for understanding then why certain programming languages, certain operating systems are more suited to wireless sensor networks and the Internet of Things. Okay, so as you know, we are now in an era where we have a completely new class of computing devices and computing applications, okay? So on one hand, we have an increasing number, let's say, of devices out there. Think about the smartphones, okay? Basically, each one of you has a smartphone, and if you compare the computational capability of a smartphone now to a top-class PC 10 years ago, probably the smartphone is going to win, okay? So we have a lot of computing capabilities, okay? And also the size of our devices is getting smaller and smaller, okay? You can easily understand this. Now, what happens is that we basically solved a lot of problems that were around. I mean, we were able to make these devices very, very small and still very powerful. We gave them the opportunity to communicate without wires, okay, so wirelessly, okay. We have a lot of technologies to do this. We have Wi-Fi, we have Bluetooth, we have 802.15.4, let's say Zigbee, okay. We have a lot of technology to do this, and if you think also about that, the bandwidth which is available is increasing, okay. So we have, let's say, better and better communication protocols and communication tools that we can use. Probably one problem that's still out there is, let's say, the energy related problems. So still we are trying to solve, or let's say to make the lifetime of a battery as long as possible. Okay, and again, I can bet that you easily understand this, because probably you have to charge your smartphone every day, right? So if you start using some application, if you use a lot of 3G, then you have to charge it every day. You cannot escape this, right? I'm a little bit older than you. When I had your age, I just had a crappy Nokia, probably, without 3G, without nothing, and it could last maybe 1 week without charging, and that was cool. Okay. Probably from the technology point of view, I mean from the hardware point of view, one of the challenges that we have now is the energy problem. Okay, so how do we optimize hardware, software, everything in order to make the battery last as long as possible? So, and we will see that a lot of let's say choices for programming the Internet of Things are basically driven by these requirements. Okay, minimize the energy consumption. So keep always in mind this. The primary goal is typically to minimize energy consumption. Okay, it will become even more clear in a couple of minutes. So on one hand, we have this technology push. Okay, so we are able to do a lot of stuff with our hardware. And on the other hand, we have new applications that are demanding new technologies. Okay, is the door open? No, it's closed. Okay. So in the last few years, we experienced a lot of very new applications, which basically required to have small devices able to communicate with other devices and other PC, able to capture measurement from the environment, and on top of which we could actually build the Internet of Things. Just to give you some examples, monitoring in general is a good application area for the Internet of Things and wireless networks. Okay, imagine to have that you want to monitor, for example, the energy consumption of the electronic devices in your house. Okay, because you want to, for example, lower down the electric bill at the end of the month. What you can do is to attach an energy meter to each electronic device, collect all the data, okay, and see what is, for example, the device that consumes the most amount of energy. And then maybe you can try to switch it off or to switch it on only when you need it. For example, think about the washing machine or stuff like that, okay. But monitoring can also be other type of monitoring. For example, if you want to monitor the status of a forest, okay, and you want to prevent fires in this forest, you can put the temperature sensor or other types of sensors, for example, infrared sensors. You can scatter these sensors in the forest, and then you can have an application that, for example, triggers an alarm when the temperature suddenly goes over a certain threshold. Okay, so you can monitor stuff, but there are really plenty of applications that uses low power devices, so battery operated devices that can last at least 1 week, 1 month, or maybe more, and that they collect data from the environment and communicate this data to some other entity, okay, for processing. There are really many examples of this. I guess I have put some in the slides as well. Okay, here. So, for example, if we go on, this is a very nice website with some interesting things about the Internet of Things, and let's try to open it. If just want to show you. These are the best Internet of Things application of the last year. Okay, so let's see what we have. So we have, you see, different categories. Let's try to see connected home, for example, what we have in this field. You have a lot of devices which were produced, and each one basically monitors something. So I can open, for example, this one. What does it do? It's a wireless sensor network that detects water leaks, for example. Okay, water leaks, changes in humidity and temperature, and alerts you if anything is amiss. Okay. There are other examples here. For example, thermostat, similar to the Nest one. I don't know if you know it. It's a simple thermostat that monitors the temperature and turn on and off your heating system according to the temperature that you have set. Everything is wireless, so it's very, very useful and easy to install and this kind of things. So if you go on this website, you can have a let's say a more updated look on what's really going on in the Internet of Things now. So what are the applications that sells, basically, okay? And as you can see, they are basically all based on this paradigm. So you have a sensor somewhere, battery operated, so no cables. The sensor measures something. It could be temperature, it could be humidity, it could be anything. And it sends this data somewhere else, okay? And then on this data, you can put some sort of advanced algorithm. You can do analysis. You can do whatever you want, logging, whatever you want. Okay. So that's what I was saying. So we have these common features here. Enter full screen, which is low-cost hardware, typically small. Okay. And typically battery operated. We have data sensing, whatever data it is, wireless communication, and then data logging or data analysis somewhere else. Okay? Why, in your opinion, data analysis and data logging, so storing data, is done somewhere else and not on the sensors? Anyone? Exactly. First, because typically they are low-cost hardware and they have probably maybe just an SD card on top if we are lucky, maybe not. So space is limited, memory is limited, right? So this solves the problem of data logging. So storing data somewhere else. And why we do not do data analysis on the sensors? Exactly. So everything that involves intense computation, large memory, or large resources in general is not performed on the sensors, okay? But it's typically performed remotely. Very good. Of course, why we are giving this course, in your opinion? Well, because the Internet of Things is coming. So, I mean, it will come, okay? We will see it sooner or later. So there are a lot of potentials, okay? And we want to exploit them. Not only, let's say, for making money, okay? That could be, right? But if you are more ethical about it, for a better living, okay? So you can think about all the applications that you can set up to save energy or to prevent disasters, okay? Of course, you want to get paid for that, right? But still, it will be a big change, okay? And of course, it's let's say it's really cool. It's flexible. We have no wires. Typically, all these applications are self-configuring, okay? So the users are not doing anything in particular. You just buy the sensor, you turn it on, and it works magically. So short time deployment, okay? And of course, numbers, okay? We expect that the number of sensors or devices, let's say, in the Internet of Things will be greater than the number of people in the world. But I mean, one order of magnitude at least. So 10 sensors per people, okay? So we have really great numbers here, okay? Scale economy, I'm talking about that. So if you create a startup that sells sensors, and then you sell, I don't know, 20 billions of sensors, then you are super rich and you are super happy. Anyway, on the downside, we have still a lot of challenges, okay? Well, as I was saying, most of the challenges are on the energy-related parts, okay? Because from the other aspect, I would say from the hardware point of view, from the communication point of view, we have several solutions, okay? Some of them are also becoming standards now. So on that side, we are pretty much okay. The problem is how to really be energy efficient, okay? So connected to this, we have other problems like, okay, how do I ensure robustness? So especially in network scenarios, when I have many sensors. Think about the forest example. You have many sensors. What happens if one fails, okay? So can I use another one to back up the dead sensor? Can I do something smart about it? So robustness is one key topic here, and then of course we will see during these lessons mostly all the challenges that we have in this world. Okay, let's see what one of these sensors looks like. Okay, so they come in very different forms. Okay. But they all share a same layout, which is the one on this slide. So you have, of course, a power unit, and typically this is a battery, okay? Typically 3 volts at least, could be also less, could be more also. Then you have, there's a processor here. Typically it's a microcontroller. Okay, so it's not a CPU, it's a MCU, a microcontroller unit. That means that we are in the range of tens of megahertz, okay, not gigahertz, tens of megahertz. We have a memory, a RAM memory, let's say, of tens of kilobytes, okay, not gigabytes like your PC or your smartphones. Then we have some sensors, okay? This could be anything. This could be temperature, humidity, pressure, CO2, whatever you want, okay? Also, more complex sensors like accelerometers, movement, video. A camera is a sensor, and other kind of stuff, okay? So every hardware that can measure something from the environment, okay? And then you have a transceiver. So the transceiver is the radio chip, okay? So you have a block that is needed to communicate with other items, other sensors, or I don't know, a server where the data is analyzed and so on and so forth. You can have also, let's say, optional component, like you can have an external antenna in order to extend the range of communication, while typically the antenna are integrated, okay, like the one that you have in your smartphone. And additionally, you can have a location system, which basically localize the sensor in an area. It could be a GPS, for example, if we are working outdoor, or it could be some other type of sensor if you are working indoor, where the GPS signal is too weak to arrive. And again, you can have an optional component which is a mobilizer, so something that makes your sensor move. It could be a little motor with some wheels that you can control in order to move your sensor to get some measurements from where you want, okay? But typically these components are optional, so mostly you do not find them, okay? So we have these four basic components: power unit, radio chip, memory and microcontroller, and all the sensors which are attached, okay? Here it's just a slide, let's say a time scale which shows some of the model out there that you can buy. It's a little bit outdated. For example, well, apart from that, it's from 6 years ago. Can you tell me at least one very, very famous device which is recent, I would say, which is made in Italy? And exactly, okay. So Arduino, it fits exactly in this kind of sensors. Okay, it has a microcontroller. It can be powered with batteries. It can mount a transceiver. You can mount it on top of it, and you can attach lots of sensors. Okay, so it perfectly fits into this design, and it's low cost. It's cheap. It's small in size, so yeah, it's there. There are other kind of stuff. Now we have this trend of microcomputers. For example, the Raspberry Pi. I don't know if you know it. It's not properly a device for wireless sensor networks. It's a little bit power consuming. Its power consumption is around 2 watts, but it shares some features in common with this. Okay, it's cheap. You can attach sensors. You can attach communication devices. So it may fit there. Let's just see the details, for example, of the Mica Z platform, which is one of the most famous platforms that are used in many research studies. So we have a microprocessor which is 8 megahertz. So 8 megahertz is really low. Okay, do you agree with me? 8 megahertz. Compare it with your PC. You have I don't know, 2.3, 2.5 gigahertz. Okay, so 8 megahertz is really low. You can have 4 kilobytes of RAM. Then you have some serial port connection for programming. The radio interface is based on the 802.15.4 standard, and it can go as fast as 250 kilobits per second. Again, it's very small bandwidth here. Okay, compare it with the Wi-Fi bandwidth of I don't know, tens of megabits per second. Okay, we are two order of magnitude below, basically. And then, of course, you have some other stuff. I will bring one of these maybe in the next lecture so you can see it. Okay. Well, this, again, you can attach to these devices a lot of sensors, and typically these sensors come in a single sensor board that then you can attach, and so you have the opportunity to get the measurements from all these sensors. Arduino as well as a sensor board like this, but you can also attach the sensor that you want directly to the analog or digital input and stuff like that. Okay, nothing really interesting. Any questions so far? No. Everything is clear, right? Okay. So let's go on the operating system side. So I've given you an overview on the hardware, basically. So what kind of devices are we using? Now, how can we operate the device? So to use a parallelism, you all have different devices with different operating systems on top of them. Okay, so I see, for example, a guy here with an Apple. And what kind of smartphone have you got? An iPhone. Okay, so you are a Mac user. So anyone that has, for example, an Apple and an Android device, okay, you. So you are using two different operating systems, for example. Okay. So the choice of the operating system is really crucial. Okay. So why choosing one instead of another? Well, let's say when you are on a PC, you can have a choice, but it's typically driven by how much nerd you are. If you decide to use, for example, Linux instead of Windows, or if you have an Apple or not, basically. Okay, so there's not this big choice. Also for smartphones, basically you are constrained to the model of hardware that you buy. Okay, so typically on Samsung you have Android, on Nokia you have Windows, and on the iPhone you have this Mac OS X. Okay. Instead, when we are talking about devices for the Internet of Things, we will see that we can choose actually the operating system to put on top of them. And some of them are better for certain types of applications, and some other for other types of application. So we actually have to know them and to decide when to use one and when to use another one. Okay. First of all, let's see what are the main features that a good operating system for wireless sensor networks should have. Okay. And let's try to understand operating systems for standard PC first. Okay, so I don't know if you have taken any course on operating system or on computer science in general, but I will go very fast on this. So typically, an operating system is divided in two parts. Okay, you have, let's say, the operating system itself, which provides all the drivers for accessing and using the hardwares, all the network stack for communication. Then you have the thread control, the scheduling, and all this kind of stuff. And on top of this, there's the user space. So all the application that you want to use and how they use the lower layer components. Okay, and there's a clear separation between these two words. Okay, and when you want to modify something here, you basically need to have administrator privileges. Okay, Linux users know this very well. Every time you put sudo, it's because you have to modify something low level. Also, Mac users know this. When you try to install something which is not, let's say, completely trusted from Apple, you have to put your password in order to modify this kind of stuff. Windows users, well, it depends on what kind of Windows you are using. In previous version, it wasn't that clear, with the result that any 1 week you have a bug to fix, basically. Okay. So in general, you have a clear separation between these two words, and you also have operating systems which are based on a kernel. Okay. So which means that you have a block of code which is actually doing as a translator between your hardware level, so all the hardware that you have attached to your PC, and the applications which are on top of them. Now, this approach is okay for PC, even if it requires a lot of resources. Okay, so it typically requires large memory and storage, You have a lot of complexity for the scheduler, address space isolation in order to not to ruin all your data. You have really a lot of complexity here. So is it really a good way to go to replicate this design for wireless sensor networks? So for devices which we have seen have very, very low resources? Well, probably not, okay? So we would like to have well, not a completely different design, but at least a design which fits better the hardware that we have, okay? So we will not use a general purpose operating system for wireless sensor network, okay? Basically because of the complexity, okay? If we want a general purpose operating system, we have a lot of complexity. To manage this complexity, we need a lot of resources, which we do not have, okay? So we come back to the beginning and we decide to not to use a general purpose operating system, right? So let's see what are the requirements for a lightweight and small operating system for our resource-constrained hardware. So first of all, we wanted to have a small memory footprint. Okay, so we wanted to weight really a small amount of memory. Okay, maybe kilobytes. Okay, not much. We want to have a low system overhead in terms of managing. Okay, we do not want to waste a lot of CPU cycles just for the operating systems. Why? Well, because we are working with microcontrollers which are slow, okay? So 20 megahertz, 4 megahertz, something like this. So we do not want to waste CPU cycles for completing tasks of the operating system. We want it to have low power consumption, of course. And we want it to be oriented to the application design, okay? So this is our main difference. So when we use one of our PC, the operating system lets you install whatever you want, okay? You have all the tools ready. When you download a new application, you know it will work more or less, okay? At least you have to install some additional package, but more or less you have everything ready on your PC. Instead, we will see that for wireless sensor networks, the operating system should give you only what is needed for the particular application that you want to use, okay? That's, if you think about it, it's straightforward. For example, if I have on my device a lot of sensors, for example, a camera sensor, a temperature sensor, and a CO2 sensors, and I want to use the device for an application which do not use the camera, why the operating system should give me all the code and all the tools for using the camera? There's no need since I'm not using it, okay? And probably if I explicitly say that I will not use the camera, I can save some resources for doing something else, okay? That's what application-oriented means. Use only what is needed. And still, I want the operating system to be flexible for implementing different types of applications. Okay, I would like it to be at least powerful enough for developing many different class of applications. Okay. So these are the requirements that we would like to have. And if you look out there and what's available, there are several solutions. Okay, I have listed here some of them. And as I was saying, TinyOS is probably the most famous one. Okay, and we will see it in details. Then we have Motrunner, which is from IBM, which has this new approach, and Contiki, which again is typically used for commercial application. Apart from these three, which are the one that we will see in details in this course, there are others, okay? So there's Mantis, NanoRK, LightOS, FreeRTOS, plenty of them. And if you go on the website that I showed you at the beginning, the one with all the Internet of Things applications, there's also a list of software which is used for Internet of Things, and you can go there and check all the other operating systems, okay? Good. Now, let's have a very, very quick outlook on TinyOS, okay? Now, this is just giving you some detail, well, details, okay? Let's say it's an overlook, okay? So don't take it too seriously. It's just to give you a flavor of what we will see in the next lessons. So, first of all, well, this is in common to all the systems for wireless sensor networks. It's an event-driven architecture, okay? It means that, and this is basically related to energy consumption, it means that the operating system in its quiet state does absolutely nothing, okay? It can go to sleep, okay? Because everything is triggered by external events, okay? And these events are typically timers, okay, that you set, or events that are coming from external interfaces. For example, sensors or radio related events. For example, a new message is received on the radio, okay? So the operating system basically respond to events by executing particular codes, okay? So particular lines of codes. And this is useful because it allows you to control what happens between an event and another event, okay? And typically what you want to do is to do absolutely nothing, okay? To save as much energy as possible, okay? So imagine an application, as I told you before, all these applications have in common 4 things, okay? They sense data from the environment, so they get data from the environment, they communicate the data with other entities. What else? They are battery operated, and I don't remember. Okay, there's data analysis on the server. Okay, so basically the device has 3 common features. It sends data, and it transmits data, and it is battery operated. So in order to save energy, battery operated, we can decide what to do between one measurement and basically one transmission, okay? So we can decide to measure the data of interest with a particular frequency, for example, one measurement every 10 seconds, okay? And we can decide either to aggregate data and send out this data after, I don't know, 1 hour of collecting this data, or every 10 seconds, it's the same. But what's happened is that in between the 2 events, we can put the system on sleep, okay? So that we can save energy. So it's an event-driven architecture. Then we have a single shared stack. What does it mean? It means that we cannot use dynamic allocation for the variables in our code. Now, are you familiar with the concept of dynamic allocation or not? How many of you are not familiar with the concept of dynamic allocation? The telecom guys, right? Yeah. No, well, when you program, you can decide where to put the variables, okay, in your code. So you basically have 2 places One is the stack and the other one is the heap. These are two different places of memory. The difference is in these two is that in the static memory, you, before, let's say, running the program, you know exactly how much space you will use. Okay, this is static allocation. Sorry. In the dynamic memory, you allocate memory, so you reserve space for your variables at runtime, so while the program is already running. What is the problem? Well, the problem is that in order to use dynamic allocation, you have to have an operating system which supports this kind of behavior. Okay, so the operating system should take care of reserving spaces for your variables, checking if you are not going out of the reserved space, checking and moving memory from one place to another place if you need some additional space, and all this kind of stuff. Now, all this kind of stuff is complex to manage. So for the very same reason, all these operating systems do not use dynamic allocation. They just use static allocation. And okay, then we typically do not have this strict differentiation between user space and kernel space, okay, as in traditional operating system. And typically, the operating system and the application are built in the same code, okay, somehow. We will see how, basically. So you don't have an operating system that is there and gives you the tools for operating the application, but when you write the application, you explicitly tell what are the components of the operating system that you want to use. Okay, this is again on the same level of use only what you need. Okay, so that we are more energy efficient, we save resources, and so on and so forth. Okay. Well, so in this sense, if we look at TinyOS, it should be clear now that TinyOS is not an operational system in a traditional sense, but still it provides a framework to implement applications, a lot of different applications for wireless sensor network and the Internet of Things. We have basically three main components in this operating system. One is the scheduler, which is the only part of the operating system which is always there, so which you always have to use. And the scheduler basically contains the logic for executing your application. Okay, so for basically executing line of codes and putting the system to sleep, reacting to events, and this kind of stuff. So the scheduler basically is the only thing that you do not control, or if you want to control it, you have really to go on a very low level of programming. We will not see anything about the scheduler during these classes. Okay, and most of the people out there, they just use the standard scheduler. Then we have two, let's say, other items: the components and the interfaces, which basically are very, very related one to the other. Now, the components are actually pieces of code that do some functionality. Okay, so a component could be the sensor, the radio chip, okay, a timer. Okay, it's a piece of software that does something. Okay, and the interface, it's basically an instruction guide on how to use a particular component. Okay, so the interface does not contain code. Okay, does not do anything in particular. It just lists what are the functionalities that a component has. Okay, so it's basically a user guide for a component. Again, I don't know if I want to go into these details now. Probably it's better that we will see. Well, no, but just have a quick look on this. For example, let's look at these two pieces of code here. Okay, these are two interfaces. I have an interface clock and an interface standard control. And as you can see, there's no code inside. Okay, it's just a list of headings basically. For example, the interface clock has one command, which is the set rate, and as you can imagine, it's used to set the rate of the clock. And it has an event which is called fire, which, as you can imagine, it will be triggered when the clock reaches what you have set. Okay? Now, command and events are the two basic items that you find in every component or in every interface. Okay, it's the same stuff. So a command is something that your application can call on the component. For example, think about a component which is the radio. A command could be send a message. It could be scan the radio for incoming messages. It could be set the power of transmission to a particular value. Okay, these are commands. An event is something that you do not control, so it's totally asynchronous, and it comes from the operating system. Okay. So an event could be, oh look, a message is arrived on the radio, or oh look, the sensor has finished doing the measurement, or there's a problem on a particular interface. Okay, so event, something asynchronous and something that you have to manage in order to implement your application. So since you have commands, which is something that you can use, and you have events, which is something that the application will notify to you, interfaces are called bi-directional. Okay, you have two directions of use. One through commands and the other through events. Okay? Is it clear? So events can be either hardware-based or software-based. Now, hardware-based are basically interrupts, okay? So they depend on a particular hardware. For example, again, there's a problem on a particular interface, or the sensor is ready. These are typically hardware events. But you can also specify software events, okay? So you can also specify an event when a particular condition occurs, okay? And this will be an event as well. Now, so we have seen we have components and interface. Basically, they are connected one to the other. An interface tells you how you can use a component through commands and events, right? And then another item of TinyOS is tasks, okay? Now, tasks are basically pieces of code that you can use in order to provide or to, let's say, do some sort of operation. And typically, tasks are used to perform intensive operations. Well, intensive, let's say, for example, if you have to sort a vector of numbers, or you have to compute the sum, or a particular mathematical function on a set of numbers, then typically you use tasks. So you use tasks for, let's say, performing long-running operations. And it will be clear why we use task when we actually see task in the TinyOS example soon. just know that we have also tasks in TinyOS. Okay? Okay, yeah, I've put some tasks. Look, we can skip these slides just because we will see them in details when we look at TinyOS. Let's talk a little bit about scheduling. Okay, as I have told you, the scheduler is something that you always have in TinyOS. And actually, the scheduler is a component that you basically have in all the operating system for wireless sensor networks, since it's the, let's say, lowest layer component of your system. In TinyOS, the scheduling controls what operation should be done and when. Okay, and as you can imagine, if I have an event, okay, that I have to manage, the scheduler will give priority to that event. Can you agree with this? So if something wakes me up, for example, a message has arrived on the radio, I have to execute code for managing this message, right? So the scheduler will give priority to events. An event is always the priority, basically. Instead, tasks, so which are these longer running operations, are put in a queue, okay, which is then controlled by the scheduler itself. So what the scheduler does basically is to look at this queue of tasks and see if there's a task that has to be executed or not. So if there's a task, the scheduler will start executing it, and it will eventually stop the task when either the task is finished or an event has arrived, okay? And then it will go back to the task after having completed the event management, okay? So as you can see, as you can see, why I have task? Because if I try to manage an event with a very, very long-running code, for example, let's think about this situation. I have an application that receives, for example, a number from the external and has to compute the, for example, factorial of this number. Okay, something like this, or something even more complicated. For example, I receive a vector of number and I have to compute the Fourier transform of this vector of number, okay? Which is something which requires a little bit of computation. Now, if I try to manage the event with this long-running computation, let's say CPU will be stuck in this computation and cannot receive other events properly. While if I take all this processing and I put it into a task, which is then executed asynchronously by the scheduler, then the system is much more efficient, okay? So I receive an event with this array of number, and I put a task in the queue saying, look, I have to perform the FFT of this array of number. So the scheduler will take this array of number and put it somewhere, and then it will go back to sleep. It will look if we have some task in the scheduler, and it will try to execute them. So in this case, it will perform the FFT. And then if I have another event that comes, now I can interrupt the task, manage the event, and then come back to the task. So tasks are used to increase, let's say, the flexibility of the system and to increase also the responsiveness of the system. And it's a good practice to put all the intense processing into tasks. We will see again this into details when we look at TinyOS examples. But this is a common feature of all the operating system for wireless sensor networks. You you want them to be flexible and responsive to external interrupts, and you want to limit the, let's say, computation that you have to do. And if you have to do it, to do it in a way that can be interrupted by events. Okay? Okay. Now, always talking about operating systems. Sorry, first of all, do you have any question? Curiosity? No. Okay. As we have seen, there are a lot of operating systems that we can use. Okay, so if you remember that list, we will see 3 of them, but there are many others. And of course, in order to learn and use an operating system, you have to pass through a standard procedure, which usually is, okay, let's download the operating system on my PC and start using it in simulation mode. Then if everything works, I can try to upload the code on a device and see how it works. Okay, this is a standard procedure that you have to do. Now the problem is that even this procedure can take a lot of time, okay, because there's no standard way of installation. Typically these systems are Linux based, so you have to know a little bit about Linux. They are not very user friendly. From the point of view of a student, maybe a TLC student which do not know a lot about programming and this kind of stuff, starting with one of these operating systems can be a little bit tricky, let's say. Okay, so for example, you can take a lot of time to install TinyOS. There are always some packages that are broken, they do not work, and so I know this because it's already 4 years that I give this class, and I know what problems can happen. For example, TinyOS. If you have Linux, then you may be able to install it. But if you have Windows, you have to pass through Cygwin, which is a system that, let's say, creates a subsystem similar to Linux in Windows. If you are on Mac OS X, it's a complete nightmare. At least 2 years ago it was. Then I never tried again. So all these issues may discourage researchers and students to play with TinyOS and also with other operating systems. So what we decided to do is to basically give you a virtual machine which is ready to be used. Okay. So what's a virtual machine? It's basically an emulation of a already prepared system that you run on top of your system, whatever system you have. Okay. So I have prepared this virtual machine. It's a Linux-based virtual machine, and on top of it I have already installed the TinyOS, Motrunner, Contiki, Xively. I've put some examples there, so you don't have to pass through the nightmare that I had to pass, basically 3 or 4 years ago. So what I ask you is to go to the IoT website, Professor Cesana's website, download this virtual machine. There's also here in the slides, I guess, yeah, there's a list of instructions on how to run it. It is based on the VirtualBox virtual machine, which is completely free, and it can be run on any operating system. Okay, so you should be able to work with it. The file itself, it's around 2.5 gigabytes, and you need at least 10 gigabytes free on your hard disk. Okay, so yeah, make sure to free a little bit of memory for that. What you will find on the virtual machine is Contiki, plus all the examples, TinyOS plus all the example, and Motrunner. So these are the 3 operating systems that we will see. Then I have put some Xively, which is this web-based application for putting the data on the web and getting the data from the cloud and so on. And we will see it in the next lesson next week. And also this Sixth Sense, which is something very, very similar to Xively, and we will look at it as well. What I would like to ask you is, if you come to the next lessons, bring your PC with you and prepare the virtual machine. I will show you now it, so that you can actually try the example why I show you. Okay, so that will be, let's say, much easier for you to understand how it works, and of course, if we have any problem, we can try to solve them on the fly. Yeah, that's it. So I can try to show you. We have 10 minutes. Okay, sorry for the timetable. I usually come at 1:30 till 3 p.m. Okay, are you okay with this schedule? So we can use this. So you open VirtualBox basically, which is this free operating system. Then you have just to go here and select import appliance, and then you import the file that you download from the website. And once you import it, you will have this virtual machine here. Check the description. Is a virtual machine containing tools for developing IoT and wireless sensor network application, and then you just start it. Okay. When you start it, a window will appear, and in this window, basically, it's like having another PC. Okay. So you can also screw up a lot in this machine. If you do something bad, then you just erase the file and download it again. So it won't affect your PC, okay? Let's wait till it loads. Switch to full screen. A little bit slow, I don't know why, probably because of QuickTime, which is recording. And the password for entering for everyone, since it's the same machine, is user, okay? And that's it. So how many of you are familiar with Linux? So, okay, pretty much everyone. Anyway, it's not that difficult. I mean, we will use it as users, not as administrators. It's quite easy. And you can, and this is basically another PC that you have. Okay, so you can use it exactly as you use your operating system, but you have the benefit of having all the tools we need already installed. Okay. Yeah, you can also, if you are brave enough, you can also check these initial examples that I have put here. Or you can wait for the lessons, so we will see everything during the next lessons. Okay, any question? So if you have no questions, we can stop here. And so good holiday break, good Easter break. And yeah, we will see each other next week. Okay?